So today we will have 5 talks, including myself. And let's move on to the next presentation. It will be presented by Professor Zhaoxia Pu from the UUtah University, and she will be talking about the application of CYGNSS on hurricane data assimilation and prediction. We can start. Thank you.
Hello, thank you for attending my talk. My name is Zhaoxia Pu. I am the professor of University of Utah from United States. My major research interests are numeric weather prediction and data assimilation. Today, this presentation, my topic is assimilation of CYGNSS data for improved hurricane analysis and prediction. So CYGNSS here stands for Second Global Navigation Satellite System. So this is one of NASA satellite mission managed by Dr. Prof at University of Michigan. He has given a talk about the overview of the mission in the previous session. Okay, in this talk, I'm going to show you some of the results we had about the impacts of assimilating CYGNSS level 2 retrieval the ocean surface wind on hurricane analysis and prediction. Specifically, I'm going to show you some of our early study with observation system simulation experiments, and also the data assimilation study and the recent studies on evaluation of the potential operational application of CYGNSS data in the numeric weather prediction, particularly for hurricane forecasts. So throughout the talk, I'm also going to cover this methodology and strategy we used for assimilating ocean surface wind. And finally, I will do a brief discussion and outlooks to facilitate discussion on the future work. So most of the results I'm going to present today have already been documented in this series of publications. So here are the first 2 paper documents, the OSSE results and the NATO 2 publications documents the data assimilation studies. So before any of the satellite launched to orbiter those days, it is required to perform the OSSE experiment. So OSSE stands for Observation System Simulation Experiments, so which is has 2 purposes commonly. The first one is to demonstrate the potential benefits of the planned satellite data, and the secondly is to assimilate this satellite data into the numeric model in order to facilitate the research and the operations in the after the mission. So here is the concept of the OSSE, specific in the regional OSSE. So OSSE begins with the natural run, which generated by the credited global model, and then to simulate the real world and provide the truth of the atmosphere scenario. And so commonly this natural run available for the global model. And so from ECMWF or from NASA EMAO. And for the regional OSSE, we generate this regional natural run from the global natural run, use a regional model with high resolution and also interested domain. Once we have this natural run, and then we can generate the simulation of the satellite observation or satellite retrieval product. So keep in mind that this natural run provides the truth, but when we generate this data, we consider the area characteristic of the instrumentation itself and also the retrieval processes. After we get the simulated data, we assimilate those data into the data assimilation system. And for the NWP model, and then we perform the forecast with and without the data assimilation and compare these forecasts with the natural run for the verification. And then eventually by compare the experiment with and without data assimilation to get idea how much impact we can get from the proposed data sets. And then of course, this whole OSSE procedure and all the tools we used will be calibrated before we get the final results. And so this calibration is just make sure the RC presents the real world problem. Okay, so this is good strategy for any mission development to get ready to use the data and also have the idea how much impact we would get from the data. The advantage of the RC is it has this natural run available, which is the truth. We know the truth. So this is good for the verification. And during the development of the CYGNSS mission, we have conducted the RC for the CYGNSS data. And so this is a sample of the simulated CYGNSS data for a hurricane case. And as you can see, different from the previous mission, the CYGNSS data not only provide the ocean surface wind in the hurricane environment, but also in the inner core region. So this is really good, and we expect this available of the inner core data will have the influence in the hurricane intensity forecast, and we will prove that. And the model we used here is UNSEP Operational Regional Hurricane Forecasting Model, which is Hurricane Wolf. And at the time of the RC, we have the novel version, so which is coastal resolution 27.9 and 3 kilometer horizontal resolution. We also use the UNSEP three-dimensional birational data assimilation system to assimilate the data, and we did a full RC, so which means not only this CYGNSS data assimilated, but also we assimilate this simulated conventional data, which is available with this community RC efforts by the time. And so as we know, this data assimilation is system try to combine its available short-range forecasting and also the observation together with consideration of the error characteristic to provide the initial condition for NWP model and also to generate the best possible estimation of the atmospheric state of analysis. So as you can see here, this is simulated CYGNSS data, and so there's error statistic of this CYGNSS data as comparison between the natural run and the CYGNSS retrieved data. You can see, so this is nicely projected the uncertainty from the satellite retrievers. And with the data assimilation, we needed to do the RC to do the QC, so the quality control. So with data assimilation, we did the quality control first, and to reject those lower quality data and keep this good data for the data assimilation. And we use the two strategies to assimilate this CYGNSS data. The one is data thinning, and the other one is super-ups. So this is in the consideration we use this coastal resolution of the model, and also consider the correlation between the data and the requirement of uncorrelated relationship in the data assimilation. So these two experiments with assimilation of the CYGNSS compared with the control run without assimilate CYGNSS data and also the natural run results. So here is a typical case we get. And as you can see here, the assimilation CYGNSS data helps the model to produce better track forecast and also intensity forecast. So specifically here, example for the minimum sea level pressure, as you can see. So this is the minimum sea level pressure from the natural run, and this is from the experiment without CYGNSS data assimilation. So this is red, and then so this blue and purple is experiment with CYGNSS data assimilated. You can see how much benefit we can gain from assimilating of the CYGNSS data, and it's significant improvement in this track and intensity forecast. So then in terms of the different methodology to assimilate data here with multiple case evaluation, we find out this data thinning helps for the intensity forecast, while the super-ups helps more on the track forecast. Okay, so this is a positive impact. And as I mentioned, so the first thing is CYGNSS data sample the inner core structure of the hurricane, and we want to see if the inner core structure would be improved if we assimilate this CYGNSS data. And the second thing is nice thing about the OSSE is because truth is available. This is give us a convenience. We can better compare the structure with natural round data, because natural round data has completed hierarchical structure. And so then with this, and we can see how data assimilation system works and how our methodology works. And then here, so showing you the surface wind and the sea level pressure comparison. And as you can see in the natural round, there is asymmetric structure of the vortices of this vortex, and also the this maximum wind location is in this side. And without CYGNSS data assimilation, we can see this weak wind and also with this less visible asymmetric, but with the CYGNSS data assimilation, we see the much stronger this surface wind and also the asymmetric structure. And we also looked at the vertical structure. Keep in mind there's all CYGNSS data available in the surface, but with the data assimilation system, we'll be able to get increment for the upper level. So we did this the data assimilation in this cycled data assimilation. So this actually makes this type of influence even stronger. So then you can see in this without the CYGNSS data assimilation, so the structure looks different from the natural round, but with the CYGNSS data assimilation, we can get the structure closer. So most impressive here is hurricane the temperature anomaly as a shaded contour here showing. So we see this inner core structure here, and also the up level warming. And so then without the CYGNSS data, we cannot seeing this structure, but with CYGNSS data assimilated, so we'll be able to see this better representation of the warm core structure. And so the impact even notable in the forecast time. So as you can see here, compare with the hurricane, the natural round, and then the control forecast and this data assimilation experiment, you can see how much the CYGNSS data can improve the inner core structure in terms of the intensity of the wind and also this asymmetric of the vortex. Okay, so the tangential wind and the temperature anomaly also get improved, and I would like to mark here. So you can see the strong up-level warming here from the natural round, and the control almost miss this part, but with CYGNSS assimilation within up-level warming is quite notable. So this is very important. Why? Because the early mechanism study showing this type of up-level warming would cause the temperature drop, and then the vortex will get intensified. But so then if miss this, meaning in the following forecast, you cannot get the deep sea level pressure drop, but with the CYGNSS data assimilation, this has been improved. So then CYGNSS data indeed improved the hurricane track and the intensity forecast, and also improved the hurricane inner core structure representation in both analysis and the forecast. And then another thing we would care about is because CYGNSS data is ocean surface wind, which has implication for the air-sea interaction. So then we checked the surface fluxes to see if there is any change in the surface fluxes after the CYGNSS data assimilation. And so this experiment proved that, as you can see, there is quite strong latent heating flux in the surface, but the control arm showing the weak latent heating flux, but with the CYGNSS data assimilation here, increment showing that there is a significant increase in the surface latent heating flux. So it's indeed a help to improve the air-sea interaction inside of the model, which is all the benefit. So then our OSSE study is quite positive, prove all these concepts, and the CYGNSS data will have the positive impact. And in the meantime, our data assimilation system works, and it helps utilize the data to result in this data analysis and forecast. So then after CYGNSS launched to the orbiter, we come to the real world to use the CYGNSS retrieved product and to see whether we can get consistent results with this OSSE results. So as you can see in here, this is our early study with two notable hurricane cases, Hurricane Harvey and Irma in 2017. So we know this is two big landfalling hurricane. It's notable events in the US. And so we used these two cases and to showing the CYGNSS data impact. And the data sets we used at the time is a fully developed C product version 2.0. As you can see here, so this is the daily CYGNSS data coverage, and there are different colors showing you the data available for different analysis cycle. So you can see we get the nice coverage from the CYGNSS data product. And also the arrow characteristic and wind speed showing that in this retrieved product, we have more no winds available, which is mostly less than 35 meters per second, and most of the wind are available no more than 20 meters per second, but the volume is quite good, and also the accuracy is quite impressive because uncertainty is low. And so we actually get this data assimilated into the HWRF model. By the time the HWRF already upgraded to the 3.9 with higher resolution at 18.62 kilometer resolution, and also has the ocean coupling capability. And the data assimilation system has been upgraded to the GSI-based hybrid ensemble 3D system. So which means this is the 3D system, but the background arrow covariances has the ensemble component to facilitate this flow-dependent background arrow covariances. So then we actually use this system, and also at the time, the operational strategy for data assimilation is vortex relocation, initialization, intensity corrector, and data assimilation. So we actually did the vortex relocation and also followed the operational procedure and then do the data assimilation. So for HWRF model for both Harvey and Irma case. And so regarding to the experiment, we running 6-hourly assimilation cycle, followed the operational procedure, and we did an experiment to assimilate the one experiment with all the conventional data, which already assimilated into the operational system without CYGNSS data. And the other experiment, we assimilate CYGNSS data. And then the final one is to assimilate all the data together, including all conventional data and CYGNSS data. So here comes an example and how the CYGNSS data influence the track and the intensity forecast. And the black is best track, and so blue is conventional data assimilation, and red is CYGNSS data assimilation, and this green is assimilation all data. So yeah, keep the story short, so we get the nice impact from the CYGNSS data assimilation for both track and the intensity forecast. So the CYGNSS data assimilation indeed helps the model to improve track and the intensity forecast. And also we looked at the hurricane inner core wind structure and to see if there is evidence the CYGNSS data assimilation help improve the inner core structure. So this is the example showing you here is a radar derived wind at 3 kilometer height. So you can see in the asymmetric structure of the vortex and with maximum wind in the east side. So then with all conventional data, you see relatively symmetrical structure in the core region with, you can see this asymmetric was not rightly represented. But with the CYGNSS data assimilation, so we can see the nice asymmetric structure in this side that matches the radar observation, and also the maximum located in the east side. So with all data together, because of involvement of the CYGNSS data, we can see this type of improvement is quite obviously. For the URMA, we get the same conclusion. So which means in the real world, we also get the inner core structure improved from the CYGNSS data assimilation. And we also checked this latent heating fluxes. And so you can see in how different for each experiment in the 6 hour in terms of the latent heating flux. And this latent heating flux difference is sustained for the longer time, because it's even in the 96 hour, you can still observe the differences in the latent heating flux from the different case. So overall, our real data assimilation experiment results is quite consistent with what we observed from OSSE, so which is good. And so this is early study, we proved the impact of the CYGNSS data. So then the next question one would ask is, so whether available of the CYGNSS data, if it is able to use in operational, what is the value of the CYGNSS data? Because in current NCEP operational practice, the ASCAT data, which is operationally available from the European satellite mission, this has already been assimilated into the NCEP model. So then the evaluation we conducted recently is to compare the impact of CYGNSS with ASCAT data. And we want to see whether CYGNSS data assimilate into the real time of hurricane forecast if it's compatible with ASCAT data. But not that, so currently CYGNSS data time latency cannot meet the operational use, but we still want to test this potential. And also time by time, and the CYGNSS data product improves. And at the time of the evaluate with ASCAT last fall, we only have the version 2.1 data available, but recently we have the version 3.0 available. So then the question here is which version of the data will have the big impact in the operational field they use? And also any hints for the better utilize of the data. So this other question we want to answer in the rest of our study. So then we pick up the newest operational version of the HWRF that was updated at NCEP Environmental Modeling Center in last fall. And the resolution for current model is 13.5, 4.5, 1.5. And so this is a high resolution, and also the GSI hybrid system still here. And so we use this GSI hybrid system. And we designed the series of experiments to first evaluate the impact of CYGNSS data compare with the ASCAT, because the ASCAT data already assimilated into the operational system. And so its configuration is already fixed there, and we don't want to do the sensitivity study with that. But with CYGNSS data, which is still did not assimilate, so we checked for the different methodology to assimilate the data. So notably, for when assimilate this ASCAT data, so they use a data thinning method. So the thinning distance for ASCAT is 100 kilometers. So then we tested for the CYGNSS data, we tested 100, so it doesn't work well. So then because CYGNSS data has this high resolution coverage in nature, so then we tested the 3 parameters. So first one is the 12 kilometer thinning distance which matches the out domain of the HWRF model, and the 25 kilometer resolution, which is matches data resolution, and also 50, so which is sending distance. So we test these three sensitivity study. And we used the Hurricane Florence in 2018 and the Mako. So these are the two notable hurricanes in the year 2018 for this test. And we emphasize on the evaluation at the landfall time, because we know the landfall in hurricane forecast is very important. And the case we choose these two major hurricane made landfall in 2018. And the hope is we assimilate this ocean surface when the hurricane over the ocean, and then we can predict the evolution of the hurricane, so get a better forecast for the landfall time. Okay. So here is in coverage of the CYGNSS data and the ASCAT data. So here the CYGNSS data as orange, and the ASCAT data as blue. And so you can see in the holder in the top three panels showing in the three analysis cycle for the Florence, how the data coverage looks like, and bottom one showing you for the Hurricane Meg case. So you can see for both of the case, we got nice coverage from both data. So the swath looks different and the resolution looks slightly different, but they're all ocean surface wind we can use. So in terms of the data assimilation results, here we checked the near surface wind at the landfall time. Here is an example showing you here the left panel is curve, which is high resolution regional analysis from the NOAA, which is the best regional analysis we can get recently. So you can see in the asymmetric structure of the near surface wind, and the result, the CYGNSS or ASCAT data assimilated, so this wind overestimate and also this asymmetric structure did not represent well. So with ASCAT data assimilation or CYGNSS data assimilation, we can see so this negative wind increment in this side, so meaning so it's makes this overestimation of the wind mitigate and also in the meantime you see asymmetrical analysis the forecast increment of the wind, and so which means we get the better asymmetrical structure. So this is even notable for the Hurricane Mako. So as far as now, so this you can see in this ASCAT and the CYGNSS made almost equivalent impact on the hurricane in the core. And in terms of the track and the intensity forecast, so it's hard to see very clearly how much impact. This is given the fact that we have larger volume of the conventional data and other satellite derived wind data, for instance, the cloud track wind and those things already assimilated into the model, and compare with larger volume of the data already available. So this ocean surface wind is small amount of the data, but even a small amount of the data, we're still seeing about 10% track error reduction from either assimilate this CYGNSS data or assimilate ASCAT data. So they equally good to improve this track and the intensity forecast. But in the meantime, as I mentioned, so for CYGNSS data assimilation, we tested the different sending distance. So what we found is only sending distance 50 kilometers would make the better forecast, which equivalent to the ASCAT data, and the other two are not. So which means we still need to properly assimilate the data in order to get positive impact. But here bottom line is the CYGNSS data makes the positive impact to the actual hurricane forecast, and its impact compatible to the ISCAT data. So this gives us much more confidence about use of the CYGNSS data in the future, possibly to have a mission like this for the operational forecast. And of course, we also check the quantitative precipitation threaten score, so which means we check to see if we get improvement in the precipitation forecast, and definitely so. For the Florence, seems like the CYGNSS data gives a better precipitation forecast, but for Mako, this ISCAT performs slightly better. So both of them have positive impact on the precipitation forecast. Okay, so then we move to the next question. So with the CYGNSS data, we have the positive impact, and then since we have different versions of the data available, so whether we get positive impact in a different version. So the answer is yes. And so then which one is better? So this is complicated. So I'm going to show you the results here. So here are these two diagrams showing you the CYGNSS data on daily available. So for the version 2.1 and version 2.30, there are two retrieved product different from the treatment of the level 1 data. So supposedly the version 3 data has better treatment of the level 1 data. And so as you can see in here from the wind speed and the uncertainty statistical. So the 2.1 data mostly stay in the no wind and no uncertainty. And the version 3.0 data, so we have the high winds represent with the high uncertainty. And also from the coverage, you can see in this 2.1 data, we get better coverage, but 3.0 data, so we get less coverage. This is maybe because of in order to sustain this, retain this high wind and some of the treatment, so get the more data rejected. Yeah, so we're not sure, I'm not the expert of the retrieval, but at least from here, this is what we can see in here. From the error characteristic are different. So in order to assimilate these two data sets, certainly, so we have to consider the error characteristic. So for instance, here for the 2.1 data, we use this error range for the 2 meters per second, but with this 3.0, with sensitivity study, we see it 3 meters per second error. So we assimilate this data into the HWRF model. Also, the parameter of the sending distance for the version 3.0 and 2.1, both are tested. So for 3.0, we tested for the 30 kilometer sending and 50 kilometer sending. And keep in mind for the 2.1, we already have idea which should use 50 kilometer sending. And so no surprise, both versions of the data gives a positive impact in the forecast. But in terms of which one better, it's really complicated because we're seeing that version 2.1 actually makes a better track forecast, and as a consequence, it makes a better precipitation forecast. And version 3.0 much more give us the advantage to improve the intensity forecast because it has a high wind represent. And we speculate that the 2.1, why it has a better influence for the track forecast is because 2.1 data will have the better coverage. And the better coverage is always helps the track forecast because environmental condition will be better. But in the meantime, the high wind representation will help the intensity forecast for sure. So then another thing to note is for the version 3.0 and 2.1, in order to get the best results, the sending distance is different because there are different versions of the data. So for the version 3.0, we finally find out the 30 kilometer thinning distance gives the best results, while the 2.1 is 50 kilometers. So this is just to conclude to our results here, and just a couple of the concluding remarks. And the first thing is from the both OSSE and the Data Assimilation Study, we see very consistently this ocean surface wind makes a positive impact to the hurricane analysis and forecasting, and those data are significant data source for improved hurricane analysis and prediction. And also CYGNSS data has equally positive impact compared with ISCAT data on the actual hurricane forecasts, which is very encouraging. And another thing to note is we have different versions of the data, so we needed to develop the strategies to assimilate each of these versions of the data, because they are come from different retrieval sources. And fortunately, both of them are made a positive impact. However, so the relative impact are complicated to comment. So then this, with these results, so I would like to comment the couple of the outlooks for the future work. So first thing is the effective assimilation of the retrieval level 2 wind product for various applications is still a valid scientific question to work, because with a different model resolution, different applications, and different weather system to deal with. So we really need to work hard to get better methodology to assimilate the data and to get the best solution we expect. And another thing is because of this retrieval process could induce some of the additional errors. So we would expect in the future we can develop the direct assimilation of level 1 data, and we want to see some of the studies in the community going on this direction. Okay, so this is all my talk. Thank you very much for your attention. I'm happy to answer your question either online now or send me email. Okay, thank you.
Thank you, Professor Pu, and thank you for sharing this wonderful, nice result and thorough investigation for hurricane prediction. And we have 5 minutes, so anyone wants to ask a quick question? I just remind that you can also put your question on the chat board. But while you are probably typing, I'm going to ask a quick question. So it seems that the data thinning is an important strategy for using the CYGNSS data effectively. So my question is that for the intensity prediction, shouldn't we expect that a higher resolution data or better coverage of the inner core that will be helpful for intensity forecast? But you recommend that the data thinning distance is 50 kilometers. So can you comment about that? Thank you.
Okay, thank you. This is good question. So the reason we have to do this thinning is because for the data assimilation system, we assume this data are uncorrelated. But during the procedure of produce the data, so they are correlated. So we have to make the thinning to make this discorrelated in order to get the better assimilation results. So as I commented here, so in a different version of the data, so the thinning distance is different. So data thinning is very important because in a real data assimilation application, we seeing this integrated data assimilation efforts. So which means the redundancy of the information will make the real damage of the data assimilation results. And so we hope the data thinning help, and also the thinning from this data assimilation results, really you seeing this data thinning is important. So that's why for the ASCAT data at NCEP operational, so they have then data singing implemented. And for these satellite retrievers, we also need to have this type of things to be implemented.
Thank you. But I thought that the analysis grid resolution in your presentation, I thought the resolution is about like it's only a few kilometers.
That's right. Yeah, that's good thoughts, because even with it is, I mean, so I would comment this data singing not only related to the model resolution. So it is related to the model resolution, but it is not only related to the model resolution. It also related to the error characteristic of data itself, and also related to the distribution of the data, and especially for the satellite retrievers, and so how the data were generated from the retrieval processes. And so this is very important.
Okay, thank you. And more questions?
Hello.
Yes, Shia.
Hi. Thanks for the great presentation. So actually, I have one question for both Professor Pu and Professor Yang. So from Professor Pu's study, she showed that data singing is very important for the R data assimilation. However, in Professor Yang's study, I think you don't use the data singing, right?
No, we didn't use data singing.
So I know different data simulation may have a different simulation strategy. But I'm thinking, do you have any recommendation for people who want to use GNSS R data for the data assimilation? Should they using data singing or not?
Professor Pu.
Let me comment on this. So I think if you only assimilate the one data type and not assimilate any conventional data, you can use whatever strategy you use. And so in that way, so when you assimilate data, as long as your data assimilation system works, you can get positive impact. But so for my study, I actually assimilate all the conventional data available with the CYGNSS data order for the integrated data assimilation efforts, because you already have a lot of information already there. So if you do not do data singing and do not work on these super-ups and this, so perhaps you are not seeing the data impact. So that's it's usually different when you only assimilate the single type of the data, or you assimilate the many data together. Because why we need to do the singing is because, as I said, in the data assimilation system, you assume this information are uncorrelated. But because you have the many data source and the information redundancy, and also during this retrieve process, so you retrieve the product, the data may correlate. So this prevent you get some positive impact. That's why the data singing is needed. So I think that my answer to you is really up to you. If you if you work on a single data set and you get a good impact and you feel satisfied, it's completely fine. But if you want to get the best, you can try the different methodology. And in the meantime, for the integrated data assimilation environment with many types of the data available, you got to work hard and on this strategy in order to best utilize the information.
Okay, I just briefly respond this question. actually we assimilate, including all the data we have, including conventional data and also the satellite, the AMV data, and the CYGNSS data. But so far, what the difficulty we have actually is that for the coverage, in terms of the coverage, it's not enough. So, and also, as you see that in my presentation, that even though we generate ocean surface wind data independently, we still see and we have a lot of data over ocean, but we see this degradation on the wind direction. So we would like to first solve this kind of difficulty first, and then and later, after all the components are set, and then we will try to see if we should optimize the use of the wind speed data. For example, whether we should do thinning or whether we should consider including the observation error correlations in our framework, which has been actually included in our radar data assimilation framework. So for that, I will also suggest that maybe we should also take a look whether and how, and for this data set, the CYGNSS data, whether there's really the error correlation, observation error correlation existed in this data set. Yeah, so that's my answer, I guess. Yeah.
Okay, so I think there should make a good comment here. So then there are two things we need to consider. The first thing is, so there's in the CYGNSS science team, there already have some of the study from the Chris Ruff's group, and they investigate this correlation between these data, and so they have some results, and we haven't really looked detail for the data assimilation. So that's the first thing. Another thing is also the data assimilation system is a complicated system. So it's really what I present mostly based on the mature system, which is already operational system. And with the operational system, there are first thing is many of the other data of the assimilation, we will not touch them. They're already there. And so then we work on what we add on. But for your case, since you work on the research model and you have different type of the data, so you have more button to tuning. So you can choose whatever the strategy you want. But my suggestion really is over the years we work on the data assimilation. For the integrate the data assimilation efforts, really, you need to consider many of these factors. So, I mean, how do you think in the data? HWRF's data, it's also rely on your model resolution and also the localization you use for your ensemble system if you use localization for the ensemble. And also what is the length scale you choose for your variational data assimilation. So I mean, there are many of these buttons to tuning, and so then I think it's data sending is important. Given for my results is given the fact that I use the operational system, and there are many other things I should not touch. But for your case, if you work on the research model, you have more button to tune, and you can find the best solution. But I mean, usually, so check with this data impact from this analysis increment is always a good idea to look how things change with you assimilation results, and then you can justify from there and to see why you get positive or negative results. And also, I think this is also the way help us to understand the science question from besides of data assimilation. So for instance, yeah, from the data assimilation in the radar data assimilation, when we conduct for the hurricane Genesis case, what we found is after we assimilate radar data, up-level warming is quite notable. And then we search the nitrate ratio, but the Professor Darlene Zhang just finished a work, and they find out this upper level warming associated with surface temperature, surface sea level pressure drop. So then this actually gives idea why the data assimilation get the better results, which also not only helps get the better analysis, but also helps understand the how the things process, helps the process study. So I mean, it's really data assimilation is a science, not only just use the data, how you best utilize the data, but also from your results, you get better or worse results. You can try to understand the processes.
Okay, thank you very much for Professor Pu's comment. Today, we are very thankful for all speakers and for the great presentation. And we just started our satellite mission for the Triton, the GNSR. And we are hoping that there will be more for this satellite in the future. So we are hoping we can keep learning from you guys and wish to catch up and with the progress like all you have. Thank you very much. So I would like to close today's session. Thank you.